Welcome back to ECE 220. You're probably getting tired of all of these announcements, but maybe not what I'm announcing. Lab 5 is now upon us, and some of you have already completed Lab 5. You will need to put your report together by next Wednesday, which is a day that we do not have class. The blue are the no class days. We will not have class a week from yesterday. Am I in the right calendar? A day before Thanksgiving, we will not have class. Lab 5 is being executed this week by Group A students. Group B, you should be getting your pre-lab put together and have available or submitted by Saturday, this Saturday, for lab number 5. And then you will have your lab, the last lab of the semester, Group B, Tuesday of next week. And we also have a homework assignment due on Tuesday, as always. That should be, I think we're in steady state by now. That's the 13th of those assignments. We will have 2 more, and those remaining 2 will be dealing with steady state, sinusoidal steady state analysis. And that's what we will talk about today. Exam 4 will be the week that we come back, and I believe the day that we come back, I'm going to go ahead and have a review session for exam number 4. The Monday we return from the Thanksgiving break, that Monday following that, I am planning a review session for exam number 4. That's the plan. And before you take off for your Thanksgiving break, make sure if you're in Group A that you've submitted your lab number 5 report. Today we're going to be playing with the tools that we are now developing with manipulating complex numbers. We'll start with just a summary or a reminder of impedance and admittance, state some definitions, and then see why we might use one versus another. We'll go through an example, and this is actually an economic example in a way. It's basically a design. It's how can we save our company money by the selection of a capacitor. And this is what you will do in the subsequent class. When you start doing power, you'll say, oh, I need to correct the power factor. We are doing that in this example by the selection of a capacitor. That will, hopefully I'll explain that more as we go through. And then we'll just start working problems. We'll see that all of this sinusoidal steady state material, which we will simply denote as AC, alternating current, we can use the same tools that we've been using all semester for the direct current or the DC analysis, where we just had constant inputs. Except now we're using phasors and complex numbers, but now we can use the same tools in AC analysis that we used in DC analysis. So now AC-DC, we can start throwing those letters around, and you can start texting those if you want. You might get some music playing if you start doing AC-DC, but you know that you're now talking about alternating current and direct current analysis. Here is our definition page, word of the day. We have 4 or 5 of those. We have impedance and admittance. Those are reciprocals, and you can break those down into their rectangular pieces. You have a real piece and an imaginary piece to make a complex number. Impedance is a complex number, admittance is a complex number if they're reciprocally related. We had R for the real part of the impedance, X as the reactance or the imaginary component, and reactance can be plus or minus, and that's what we're going to be playing with to try to find this C. The fact that we can actually add in some negative to get rid of some positive. Some algebra, essentially. We can have real part and imaginary part for the admittance, and that's G and B. So I overheard a conversation walking into work today, and she said, it's never too early to be in a good mood. So, I don't know, the G reminded me of that. So, whatever. Let's be in a good mood today, but we now have G for conductance and B for susceptance in the admittance if we want to denote those or refer to those by letters. And don't hold me to that knowledge. I'll probably not know that, but I do know impedance, and I know what that is in terms of R, L, and C. We can use our same ideas in combining impedances as we did with combining resistors. If they're in series, especially with 2, it's just Z sub 1 plus Z sub 2. Likewise, if they're in parallel, we had the product over the sum for resistors in parallel. Now if we have impedances, now just realize that Z1 and Z2 can be complex. Now that's why you have to be able to manipulate complex numbers. You're going to be multiplying, adding, and dividing just to find a parallel combination of impedances. Oh. Is that why I was getting some interesting looks? It's Z1 times Z2 over Z1 plus Z2. The structure and the formula shouldn't have changed in going from R's to Z's. Please correct me if you see mistakes. And in general, if we have a string of impedances, now we just add them all up to obtain the equivalent impedance between two nodes, node A and node B. We just say, oh, these are a bunch of complex numbers. You probably want them in rectangular form. Then you just add their real parts and add in their imaginary parts, and now you have the R and the X in your effective impedance between nodes A and B. In parallel, it's actually easier now to think about admittances. Now admittances add. So now if you had this big collection of parallel impedances, you might actually want to express that impedance as an admittance and then add those admittances, and then at the end, if you wanted to, you could say, oh, I need the equivalent impedance of this combination. You would just invert Y sub AB. But to combine those impedances, you could just add their admittances and then invert at the end if needed. And we're actually going to find admittances from impedances so that we can combine some parallel branches and make our analysis a little cleaner or easier, since we will just be adding and not having to worry about this product divided by the sum, etc. All right, so here is our first example. Find C, find the capacitor such that the current being supplied by this voltage source is in fact in phase with the voltage source. We now want to find a value of C that would allow I of t and V of t to have the same phase. What you can be thinking of while you're sketching this is you could be trying to connect this with a real system, and you might say, oh, you know what? this is really how I'm modeling. This is the impedance that my motor is presenting to the power company. I have this huge motor, and it now, to the power company, looks like 6 ohms in series with 27 millihenries because of all the wire in the coils and the wrappings. So now you have 6 plus J 27M, and you're actually trying to reduce the cost of powering that motor. And so you're saying, you know what, maybe if I connect a capacitor across those 2 leads close to the load, close to where I am, the power company won't have to supply as much current as if that capacitor was not there. So let's see if we can make sense of that. And before we do that, let me just make sure we're all on the same page. If I of t and v of t, those time domain sinusoids, are in phase, then how are the phasors, or what can we say about the phasors? Do they have the same amplitude? Not necessarily. They could, but what do they share? If I and v are in phase, that means that our sinusoids are aligned. The peaks and valleys are at the same instant of time in the steady state, in sinusoidal steady state. Our phasors then, V and I, have to have the same angle or phase. So now I was looking for, if V was at an angle, if V bar was V at an angle of theta, then I bar needs to be some I, some magnitude, at the same angle theta, in order for little I and little v, the time domain sinusoids, to be aligned or in phase. Now, before we go into trying to find C immediately, let's do some preliminary work. Suppose that for comparison later on, we want to say, what is this current I of t when C isn't in the circuit? And this is one way to sort of think through the problem. If you're asked this question and you go, I'm not sure how to analyze that, well then let's make it easier, and we're making it easier now by removing the capacitor. If we remove the capacitor, what's the circuit look like in the frequency domain? Have we changed the circuit completely? Structurally, it's going to look the same. It's just we don't have that capacitor. What's the R come in as? What's its value? If we're now in the frequency domain, we don't change the resistor. Its impedance comes in as R, as 6. What's the impedance of the inductor? Do we have enough information to find the impedance of the inductor? That's just J omega L in the frequency domain. We have J. Omega was 1,000, and L was 27 milliamps. The impedance of that inductor now is J27. And what is our voltage source in phasor form? We know its amplitude is 4. What's its phase? It's not offset, so it's 0. We're good with just then saying this is now 4 at 0 degrees. And we are really just asking to find what is this, and let me call it I1 since I've now modified the original problem. Let me call this I1 phasor, because the I is actually the situation where we're going to put the C in there. So now let's say this is I1, and I think it's pretty clean or clear what that phasor should equal. This is now Ohm's law with this series impedance. We now can say that I1 as a phasor is the voltage divided by the sum of the impedances, which is 6 plus j 27. You can now solve this however you feel comfortable solving it. But for now, let's just solve it by converting the rectangular form to polar form in the denominator. We have the magnitude as the square root of 6 squared plus 27 squared. 27 is much bigger than 6, so this ends up being 27.66, and the angle, so now I'm simply doing, I've done the magnitude and now the phase. Now just sort of envision this 6 plus j27 in the complex plane. We've gone vertical 27 and over 6. We can now find the angle of that, and that ends up being 77.47 degrees. We can write that as a complex number in polar form by dividing the magnitudes. We now have 4 divided by 28 roughly, or 1/7, which ends up being 0.145. And what's the angle? We're taking the angles upstairs and subtracting the angles downstairs, because those are really just complex exponentials, e to the j0 over e to the j77. And we can combine those exponentially so that now we have minus 77.47 degrees. If that's the case, what is this current, or we'll call it I sub 1, in the sinusoidal steady state? Can we now write that down? We know its magnitude. It comes directly from the phasor. Cosine, and this was now shaking at, did I say? Yeah, I think I did. It was 1,000, wasn't it? Radians per second, minus 77.47 degrees. Is this current, I sub 1 steady state, in phase with V? Are the peaks and the troughs aligned? No, they don't have the same argument. They don't share the same phase shift. So hopefully it's clear. Obviously, I sub 1 steady state of t and V of t are not in phase. So what we want to do is now we want to insert or introduce this capacitor to see if we can change the imaginary component of the impedance seen by the source such that that imaginary component disappears, that it's gone, by the appropriate choice of C. That's what we're trying to do. We now want to introduce C. And the idea is that we want the impedance, we want Z, seen by the source, to be real. Oh, let's be real. No, I'm meaning it shouldn't have a reactive component. The reactive part of Z is supposed to be 0. That's what I'm meaning by having Z be real. We just want Z is equal to R. We don't want a JX piece. That's the idea. And that will then allow us to say, since we know that V from our source is related to the current through that impedance Z, if V bar and I bar are in phase, what's that mean relative to Z? Or we could say, we could look at this and say, oh, the phase of V bar is equal to what? Relative to the phase of this ZI product. Can we make an expression for that? The angle of this voltage phasor is equal to what relative to the angle of ZI bar? How do angles combine? Multiply? Do they divide? Do they subtract? None of the above. They add, don't they, in a product. So this is really the angle of Z plus the angle of I. And if we want V and I to be in phase, then we need the angle of Z to be 0. And if Z is equal to R plus JX, how do we make the angle of Z be 0? We want X to be 0. Now, if somebody said, yes, but I was using admittance, not impedance, I was using admittance, well, if you now had Y, which is 1 over Z, Y is now G plus JB. How do we now want the same thing. We want the angle of Y to be 0, which means that we want B to be 0. If we have our effective impedance or admittance expressed as impedance or admittance, we either want X to be 0 or B to be 0 in order to make the impedance seen by the source to appear real, to appear to be just a resistor. We want the power company, no matter what we're doing over here with our motor, we haven't changed the motor. We still have a motor. It still has an impedance component, but we want to now attach across its terminals a capacitor so that now the power company over here, all it sees is what looks to be a resistor. Even though over here what's happening is we have an impedance from the motor and an impedance from the capacitor, but those two are playing locally and they're cooperating to actually look like they cancel each other out to the power company. That's the idea. Here's what we have. We have the 6 and we have the J27. What's the impedance of the capacitor? Just in general, what's its formula? 1 over J omega C. And we know omega, but now we are looking in here and we're saying what's Z look like to the source? These terminals are now connected to the source, or we might be saying, since we're in parallel, maybe we want to look at Y. Now I'm saying let's combine these into a single impedance or admittance. Let's call this Y2, and this piece let's call Y1, and now we can combine those. Since they're in parallel, we can just add Y1 to Y2. And it might be easier to add versus trying to multiply and divide all of these crazy complex numbers. Since we had this parallel combination, that's how we're attaching the capacitor. we're going to address or approach this problem by using admittances. So now, if we have admittances, in parallel, they add. That's the beauty of using admittances. Y1, what is Y1? Well, that's 1 over Z1, and Z1 was 1 over J omega C. So the denominator of the denominator actually comes upstairs, and Y1 is J omega C. Y2, that was 1 over Z2, and Z2 was 6 plus J 27. And now, since you have a 1 upstairs, it might be just as easy to multiply by 1, where 1 is a ratio of the conjugate of what's in the denominator here. Then you don't have to go and say, okay, I need to put that into polar form, then do my division, subtract the angle, and maybe I actually need it eventually in rectangular form. Let me just keep it in rectangular form by saying, oh, I can multiply that by 1, which is just a ratio of a complex number. What do I get downstairs? Because of the multiplication by the conjugate, I get the real part squared plus the imaginary part squared. The cross terms in FOIL, first, outer, inner, last, the OI, the OI, they cancel. OI. We now just have first, which is 6, and the last, and we square those. And upstairs we still have 6 minus J 27. Now we simply have to divide those two parts. This is a pretty good sized number. This is 765. So we divide 6 by 765 and we get a pretty small value. It's 0.007843. I'm going to forget the milli. I'm just going to keep all the significant digits, or my decimal place, hopefully in the correct location. And the imaginary part's a little bigger. It's 0.03529, and the units on that is Siemens. Now we have Y2 and we have Y1. Y1 has this unknown C, and that's what we're trying to find. Omega we know is 1,000, but we can combine those two Y's. We're really looking for the effective admittance seen by the power company. We now say, oh, that's Y1 plus Y2. Or that's now this J omega C plus Y2. And what are we wanting to have happen? We want Y to be, we want Y to look real, to not have an imaginary component. And we have an adjustable parameter. We have our C. Omega is fixed. That's 1,000. But C we can go obtain. We can find a capacitor. We're trying to find what's the magic capacitor value C to make that imaginary component go away. We're trying to make this equal 0, and that was what we were calling B before. It was G plus JB for Y. We want that component to be 0. Now we know that omega c minus 0.03529 is equal to 0, or c is now equal to where omega was 1,000. And this now becomes moving my decimal place over 3 steps to the right upstairs. I get a 10 to the minus 3. I get another 10 to the minus 3 by dividing by 1,000. I now have 35 microfarads for that capacitor. And with C equaling 35.29 microfarads, my Y now is purely real. My Y is the 0.007843. And if I'm not used to thinking in terms of admittances, I can take that reciprocal to find the impedance. The impedance now that the power company is seeing, that's the parallel combination of the capacitor with the series R and inductor for our motor. This is now 1 over Y, which is going to end up being 127.5 ohms. Just dividing 0.007843 into 1. Our circuit now is simply this, where our source hasn't changed, but now this is what we're trying to find. We're trying to find I, and Z is a real value. That's 127.5. The phasor for I is now Ohm's law, V divided by Z, which ends up being 0.0, kind of a pi sitting in there. I guess I'm hungry. 3.14 with the decimal. We're close to Thanksgiving, okay? So I guess maybe I'm thinking pies. You do not have to come to class in a week. So in a week, you can enjoy a pi in a different version than 0.0314 amps. But where are we going with this? Besides, we're in the frequency domain. We want to go back into the time domain. What is the current I that the power company is having to supply to us now that we've attached that capacitor across our motor's terminals? What's little I of t in the time domain? What's its magnitude? Now we're back to this original problem. We found a C. C was that 35 microfarads. We've put that in, and now we want to find little I of t in the time domain. We know that we're exciting or supplying this with 4 cosine of 1,000 t. And the power company is not going to be giving you sinusoidal voltage at 1,000 radians per second. It's about a third of that. It's 377. If you go 2 pi f, and f is 60, then omega is about 377. Not 1,000, but just humor me with this idea or the concept. What is I of t? We have 0.0314 cosine. What's the angle? What's the angle of our phasor I? It's not there. So we have just a pure cosine waveform without a phase shift. And this is in phase. So now we can say, oh, I of t and our supply voltage V of t are in phase. Do you remember what we had for the magnitude of little I sub 1 of t? Let's compare the magnitude of I of t. This is now, what do I want to just say? I and I sub 1 steady. And this was steady state as well. This I think I was calling I1 bar. This one was the pi with the shift in decimal. What was I1's magnitude? Quite a bit larger. 0.145. Almost a factor of 5 bigger. How did that happen? So now, this is the current magnitude that the power company has to supply. Now that we've put that capacitor across there versus the 0.145. Now they don't have to give you the magnitude of current that they were requiring before. So they're not going to charge you as much. So it's in your best interest to do this power correction or this introduction of C in order to make the current and the voltage be in phase. The power company is not happy when your load causes a big phase shift. They want the voltage and the current to be aligned as much as possible. And that difference is called, in a way, the power factor. And you want to now make your angle 0 so that you have a power factor of 1. But here, this 0.0314 is what the power company supplies. So the power company supplies much less current when we have the capacitor introduced. And we were now thinking, so now up here, we have a lot less current amplitude than what we had here. And that's a good thing. Now we can save money and we can impress our boss. We can say, oh, look at how much I'm saving the company I went out and bought a capacitor bank. I've now purchased a capacitor and now I'm switching it so that the power company sees or effectively has a resistor hanging on its lines that we are demanding power for, and we're still operating our equipment. That's because the capacitor and the inductive part of the motor are playing nice with each other and they're cooperating. They're sharing currents at the load side and the power company is oblivious to that. Let's look at let's look at another problem. Find the voltage V1 of t in this AC circuit. AC, just think sinusoidal steady state, alternating current, given I sub A of t, and here you can see I sub A of t is some cosine in milliamps, and I sub B some cosine in milliamps, and here's the circuit. And I know that you're just dying to solve this because it looks like you want to do some kind of analysis, and we can. We can use mesh current analysis or node voltage analysis just like we were doing with DC circuits. It's just now we need to push this into the frequency domain and play with complex numbers and phasors for our sources, and then we'll be able to run with that analysis using algebra and then back out what we need for the final answer. We're trying to find what's the voltage across that 1 ohm resistor on the lower left in this circuit with the appropriate current sources in play. 1.5 cosine of 2t milliamps and square root of 2 cosine of 2t minus 45 degrees milliamps. Let's put this into the frequency domain with a frequency domain circuit. The current sources are going to be as they have been. We have an inductor. We have another current source. We have a capacitor. We have 2 resistors. I sub A was 1.5 at 0 milliamps. I sub B was the square root of 2 at minus 45 degrees milliamps. This, I think, was 2. We're interested in V1. And this was J. Omega was 2. L was 1, so that's just J2. C was 125 millifarads. And now we have 1 over J 0.25, or this is now 1 over J 1/4. This is now minus J4. Now we have our circuit in a form that we should be able to analyze, and I've already given you an idea as to how you might want to analyze that. Mesh or node voltage. If we use mesh, we have 3 meshes. That's M-E-S-H, not M-E-S-S. M-E-S-H, mesh current. Let's call this one I1 and this one I sub 2. And why did I not worry about the top one? It's fixed, isn't it? That's I sub A. So wherever that mesh enters into our equations, we just write it down as I sub A bar or 1.5 M. It's a milli. Now what? We we've got 3 meshes. We don't have to worry about the top mesh. That's given. That current's given. That's I sub A. That's a source. What if we start doing a mesh analysis in the lower left mesh? What happens? Do we know the drop across that middle source, current source? Oh, great. Now what do we do? Do you remember? You guys don't even probably know about phone booths, do you? You're so young. But Superman used to go into, well, Clark Kent used to go into the phone booth and come out as Superman. Maybe we need some superheroes to solve this circuit. Some super. Is that hinting away? I wasn't going to draw a phone booth on here to give you a hint. You know that you wouldn't have even known what I was trying to draw. What are we doing? If we're doing mesh analysis, super mesh. And we can now do a super mesh down here. And that now avoids having to know what the drop is across that source. That source is just going to give you whatever voltage is needed to make sure and supply I sub b as the square root of 2 at minus 45 degrees. Let's now write the super mesh equation. Starting in the lower left, we now have 1 times I sub 1 bar. These are phasors. Plus, now we have to worry about the drop across that inductor from left to right. That's the direction we're going with I1. We now have J2, the impedance of that, times what quantity? I1 minus I sub A. We now have plus J2 I1 minus I sub A. Then we go over with our super mesh into the lower right hand mesh, and now we're worrying about the voltage dropped across from left to right, that impedance minus J4. So we just keep that collected or contained inside some parentheses, and we just say, oh, I have an impedance, but it's minus J4. Let me not worry about the minus sign. I just have an impedance. That's minus J4 times what? To give me a drop from left to right. I2 minus I sub A. Plus 2 times I sub 2, and then I'm back to where I started. That's the super mesh. And I can get rid of, these are known, these are 1.5 milli. I can put those on the other side, and let me collect my I's. I have a real part plus a J2 scaling I1. Scaling I2, I have a 2 plus a J2 minus a J4, 2 minus J4I2, and now I need to take 2 times 1.5, that's 3M, and that's with a negative sign, and I take the 1.5 times 4, that's 6, but I have my negative signs canceling on the left, so I'm going to have to subtract that. I have a J3 minus a J6 milli. Are we okay with that? Or this we could say is J minus 3 times 10 to the minus 3. Or we could pull that minus out and say this is now minus J times 3 times 10 to the minus 3. That's what that combination of I1 bar and I2 bar are equal to. I have one equation in terms of two unknowns. How do I get rid of, or can I find another equation? I have my constraint equation, which is because of that super mesh, I better have a constraint equation. That constraint equation I can find by realizing that the current source, the vertical current source, effectively is I2 bar minus I1 bar. My constraint equation now allows me to say that I sub B is I sub 2 minus I sub 1. And I sub B was this square root of 2 at minus 45 degrees milli. And if you invoke Euler or just put this into rectangular form, you can say, oh, that's square root of 2 cosine of minus 45 plus j sine minus 45. Cosine and sine of 45 are 1 over the square root of 2. Or this now ends up being 1 minus j1 milli. We'll pick up at that point tomorrow or somewhere close. Maybe you'll already have this solved. I know you're dying to get home and work this problem. You're anxious to get out of that phone booth and figure out how to solve this problem. We'll pick up somewhere close tomorrow.